These are motion with constant acceleration in 2-dimension notes. If you would, pause the video and copy these into your notebook on the next right-hand side. And then in a second I'll unpause it and you can, or I'll move it up and you can continue copying your notes. Okay, you should be done. Go ahead and copy those down at the bottom. Okay, let's go over these. We've got motion with constant acceleration in 2D, and really what I'm saying here is that motion in 2D is just really the same thing as motion in 1D, except you have an extra step. You have to break motion with 2D problems into 2 one-dimensional problems. As you saw in the Angry Birds video, the motion horizontally for the Angry Bird was motion with constant velocity, and the motion for the Angry Bird vertically was motion with changing velocity. The velocity of the Angry Bird vertically started out positive. It reached its maximum altitude where its velocity was 0, and then the velocity turned negative and began to increase. Most problems that you're going to get are going to be already broken into 2 one-dimensional parts, but sometimes you have to break 2-dimensional vectors into 2 one-dimensional vectors, and you do that using trig. We covered that at the beginning of the year. Here's an example. If I have a vector, an initial velocity of 50 meters per second at 10 degrees, I can find out that initial velocity vertically and horizontally using trig. Use the cosine function to find the x component of the initial velocity, and use the sine component to find the y component of the initial velocity. All right, next we're going to do an example problem, and you're going to need to copy this down into your notebook on the left side of these notes. So go ahead and pause your video and copy these down, and then we'll go over how to solve this. Okay, you should have it written down, and whenever you solve problems that are 2-dimensional, you need to somehow enumerate each dimension. And I like to make 2 columns and have really the givens, the unknown, the equation, substitute, and solution for each dimension in a separate column. So for this problem, we have a pool ball that's going to travel horizontally and vertically. And so my 2 columns are going to be horizontal and vertical. Or you could say x and y. The y would be vertical. Okay, so I'm going to say h for horizontal and v for vertical. And then I'm going to write my givens, g, and then I've got d0, d1, v0, v0, v1, a, and t. And d0, d1, v0, v1, a, and t. Okay, and also when you're doing these problems, it might be good for you to draw a picture. And so we could draw a table, and we could show a ball on the edge of the table, and it's moving. This ball's moving. It has an initial velocity, and it is going to go up, and then it's going to come back down again. That's what its motion is going to be. It has an initial vertical, this is horizontal, and vertical velocity. So that's its initial velocity right there. That's its total initial velocity. Okay, so let's go through, and we've read the problem, and we'll go through and reread it, and each time you come to a variable, you stop and you write it down. A pool table leaves a 0.6 meter high table. That's vertical. Height is vertical, so I'm going to say that the initial position of the ball is 0.6 because it's on the table. And when it reaches the floor, it's at 0. Now this has made me put my origin, my y axis, and my origin at the bottom here. This is my That's my origin right here. And I said that it starts out at 0.6 and it ends up sometime later at 0. Notice it doesn't go directly to 0. It goes up first and then comes back down. And it has an initial velocity of 2.4 times 10 to the, or at 20 degrees. Sorry, got to turn this alarm off. Can you go in and tell her time's up? So we've got a velocity of 2.4 meters per second at 20 degrees. And we know that's two-dimensional because it's got an angle measurement. So we can find out the horizontal and vertical component by using trig. My horizontal component of my velocity is going to be 2.4 meters per second times the cosine of my angle, 20 degrees. And my vertical component of the velocity is 2.4 meters per second times the sine of 20 degrees. So if you put that into your calculator, and we take 2.4, and then we take the cosine of 20 degrees, and we find the product of those two numbers, you get 2.26. Thank you. .26 is our initial horizontal velocity. And our initial vertical velocity is going to be 2.4 times the sine of 20 degrees. And I got 0.82 meters per second. Now, it doesn't say what the final velocity is in the problem. The next thing it says is predict the time required. So we're looking for time. That's an unknown. And we're looking for the horizontal distance. That's D1 horizontal. Okay, any other information that you know that's not mentioned in the problem? What makes the ball speed up in the vertical? Yeah, the force of gravity makes the ball speed up in the vertical, and the force of gravity pulls down, and the acceleration due to gravity is 9.8 in the negative direction. Yes. The force of gravity pulls down, and so the direction of the acceleration has to be the direction of the net force. And so the net force is down, it's negative, therefore the acceleration due to that force also has to be negative. Okay. So we have our givens, and we have our unknown. Horizontally, it does not mention air resistance. It doesn't give you a value of anything pushing or pulling in the horizontal direction. And so the acceleration horizontally is 0 meters per second squared. This is a big stumbling block for students. They want to put negative 9.8 both horizontally and vertically. And acceleration due to gravity is only in the vertical direction. Gravity pulls down, not sideways. Okay? So you might put an asterisk next to this. Don't do this, because that's a lot of students will arbitrarily put 9.8 as the acceleration both horizontally and vertically. Okay. So here's our place for our equations. Now we need to find time. Now if you go through these variables, you will find that you can only solve for time in the vertical. You do not have enough information to solve for time horizontally. No matter how hard you try, you can't do it. And so you will find the time vertically. Now, is the time vertically when the ball hits the ground the same time when the ball reaches its maximum horizontal distance horizontally? Yes. When the ball hits the ground vertically, it stops moving horizontally through the air, and the problem is over. And so time is the key to projectile motion problems. This is a projectile motion problem. And 95% of projectile motion problems ask you to solve for time first, and then some other value. So we're going to solve for time first. You have a question?
I was going to ask why the V1 wasn't any unknowns, but I think, is it because the question doesn't ask for it?
Yeah, it doesn't ask for it. Yeah. Now, but you do bring up a good point. We need to look at our horizontal, and we did not write down a D0, and it doesn't say where the starting point is, but when I drew my little graph here, I put on the x-axis, I put the starting point at the origin. And so we can say that D0 is 0. You're the problem solver, so if they do not stipulate where D0 is, absolutely make it 0. Also, if there is no acceleration, then V1 is equal to V0. So horizontally, the velocity is constant. So we can say this V1 is also 2.26 meters per second. Now, we're not going to use V1, so it really doesn't matter whether we have that written down or not, but that is one thing you can fill in. We're going to solve for time, and we do not have enough information here to solve for time in any of the equations. So I'm going to go over here to my vertical side, and I'm going to solve for time in the vertical. And I'll get out my equations, and I'll look for an equation that I can solve for time. Do I know D1 vertically? Yes. Do I know D0? Yes. Do I know V0? Yes. Do I know A? Yes. I can use the first equation to solve for time. So I'm going to write that down. And I've got D1 equals D0 plus V0 times T plus 1/2 AT squared. And then I'm going to substitute. And I have 0 meters equals 60 meters plus 0.82 meters per second times T plus 1/2 times minus 9.8 meters per second squared times T squared.
Why is it 60 meters?
0.6. Yeah, that'd be a big table, wouldn't it?
Yeah.
Yeah, 0.6. Now, a lot of students will look at this problem and they will go, man, this is a mess. But then a little light bulb will come on and they'll know that they have the tools to solve this problem. What tool can you use to solve this problem? Solve for T. The quadratic formula. It's a quadratic. So that's why you learn the quadratic formula, so you can actually solve these problems.
So we can solve this problem.
Yes, so you can solve this problem. Okay, so we're going to rewrite this in terms of ax squared plus bx plus c equals 0. We're going to define our a's, b's, and c's. So in this case, I'm going to rewrite 1/2 times minus 9.8 is minus 4.9 t squared plus 0.82t plus 60 equals 0. So A equals minus 4.9, B equals 0.82, and C equals 60. Yeah, thank you. Keep wanting to make it 60. 0.6. All right, so T, in this case we're solving for T instead of X. T equals minus B plus or minus the square root of, that's not right, minus B plus or minus the square root of B squared minus 4AC all over 2A. Yes. I memorized that when I was like 14 or 15, I guess. You never forget it. You'll remember it the rest of your life.
I hope not.
Yeah, you will.
At one point, I'm just like, I don't need this.
Nah, you'll remember it. Might get a little rusty, but you'll remember it. Okay. So let's plug in. T equals minus 0.82 plus or minus the square root of 0.82 squared minus 4 times minus 4.9 times 0.6, all divided by 2 times minus 4.9. Okay. So now if you want to, you can use your calculator. What I would suggest, though, is that you write some of this down on paper. Like, for instance, you could find this product here and write it down, and then you could square this and write it down, and then you could take the difference and write it down. And then if there's a problem, if you get a weird number, like you get 2 negatives, you have something to work with. Okay? All right, so if I plug this into my calculator, I get T is equal to minus 0.276 seconds and 0.44 seconds. Okay? Okay, now, can we have negative time? No, time's never negative, so this is nonsense. This is our answer.
Like the future.
Wait, how did you get to
Pardon me?
How did you get to the variables?
Well, because it's plus or minus. Remember, with the quadratic formula, you get 2 roots. There's 2 roots, and one of them is negative, and so that's a nonsense root. One of them's wrong. Yes.
That 4, like, it distributes to the 4.9 and the 0.6, right?
Right, this is, yeah, just it's the product of 3 numbers. 4 times minus 4.9 times 0.6.
Okay, because if you put it in your calculator like that, it just goes to the 4.9, right? Like
Yeah, you can multiply in any order. Yeah, that's a good point. Yeah, you can multiply it 4 times 0.6 times minus 4.9. You can. That's one of the properties of multiplication. It doesn't. A times B times C equals B times A times C. Same. They're the same product. Okay. So now we have the time, and we know that when the projectile hits the ground vertically in 0.44 seconds, it also stops traveling through the air horizontally. So we're going to take this number and go back to our unknowns, and we're going to solve for D1 horizontal using 0.44 seconds. So we're going to go back up here to the top and write down 0.44 seconds, right, which we've plugged in up here. And we're going to solve for D1H. We're going to look back at our equations again. There's a couple of equations you can use. I'm going to use the same one. Notice the last term, this one, is 0. When A is 0, that whole term is 0. So we really just have D1 equals D0 plus V times T, which is motion with constant velocity. It's a linear equation. So I've got D1 equals 0 plus 2.26 meters per second times 0.44 seconds. And if you multiply those together, you get D1 equals 0.994 meters. That's our second answer. Okay, so the trick is, the key to these problems, break the givens into the two dimensions, horizontal and vertical. It's two one-dimensional givens, and make sure that you don't write the acceleration due to gravity in the horizontal dimension. And then think about time. Time is a scalar. It's the only scalar in our givens, and that means it doesn't have a direction. It's not vertical or horizontal. And so when the object stops falling, it also stops traveling sideways. And that's what we figured out here. We figured out, well, when does it reach zero? When does it reach the ground? Okay, now we know that it's going to stop traveling horizontally in that amount of time.